So today we're going to talk about eigenvalues and eigenvectors. And also hopefully some repeated matrix multiplication. The general idea here is the following. When you multiply a matrix by a vector, you get back a vector typically. For example, take the matrix 1, 2, 3, 4, and you multiply it by the vector, I don't know, 3, -1. We get back a new vector. 1 times 3 plus 2 times -1 is going to be 1. And 3 times 3 plus 4 times -1 is 9 minus 4, which is 5. Notably, maybe not notably, but worth mentioning, these two vectors, let's call this, I don't know, W. Vectors V and W point in different directions, have different magnitudes, right? V looks something like over 3 down 1. And W is over 1 up 5. Certainly different directions, certainly different magnitudes. What's special about an eigenvector of a matrix is that when you multiply the matrix by its eigenvector, the direction is preserved. So eigenvectors are special. A matrix multiplied by one of its eigenvectors results in a vector in the same direction. I should say in the same or opposite direction because maybe it turns around. For example, the matrix A equal to 3, 6, -1, -4, along with the vector V equal to -6, 1. If we multiply this matrix by this vector, A times V is going to equal 3, 6, -1, -4, multiplied by -6, 1. Let's see, we get -18 plus 6, which is -12. And we get 6 minus 4, which is 2. And if you notice, that is exactly 2 times the vector we started off with. So in this case, multiplying the vector by the matrix A preserves the direction of the vector. It's still pointing in the same direction. It just happens to have a different magnitude. So if we were to draw this, I don't really want to draw it, I'm going to draw it. So I'll point out if we drew this, our original vector V would be 6 left and up 1. So I'm not drawing it very well here. So there's our original vector V pointing left 6 and up 1. And then we're just doubling it to get A times V. Sorry, those should look like they point in the same direction. They do point in the same direction. Again, the point being that the matrix times the vector just changes the length, but not the direction of the vector. Let's see, what else do I want to say about this? Yes, so the real point here is how do we find these things? So how do we find eigenvalues and eigenvectors? Oh, I would also point out, so just for some terminology here. So in this example, V is the eigenvector. And it's the eigenvector associated to the eigenvalue, which is 2, or the multiplication factor. It begs the question, how do we find eigenvectors in that, or eigenvalues and eigenvectors? And I say this in this order because we almost always find eigenvalues first. Yeah.
Does the eigenvalue remain constant?
No, it does not. So I would say that for any matrix, it's going to have specific to it eigenvalues and eigenvectors. And each eigenvalue, which we find, will have an eigenvector that is associated to it. And the eigenvalues can be anything. So usually for each matrix, you will find some number of eigenvalues, and typically the number is the number of rows or columns in your square matrix. So we're going to mostly be dealing with 2x2 matrices, and most 2x2 matrices we see are going to have two distinct eigenvalues associated to each of them, two distinct eigenvectors. There are some exceptions, but that's usually what's going to happen. So here's the idea. We're trying to solve the situation where the matrix times the vector equals a constant times the vector, or a multiple of the vector. So we're trying to solve a times the vector equals a constant, which is usually called lambda. That's the typical letter for an eigenvalue. And so here's what we're going to do. We're going to bring everything to the left-hand side. And I know he talked about this like the end of class on Friday. So to solve this, we're going to bring everything to the left. So a times v minus lambda times v equal to the zero vector. The problem with this is that you can't just factor out the v here because a minus lambda doesn't make sense. A is a 2x2 matrix or some matrix, but we're thinking 2x2. Lambda is a scalar or a number like 5. So to make this work, what we do is we multiply lambda by the 2x2 identity matrix. If you want to kind of think of this more broadly, so you can see what we have here is we have like the matrix A, B, C, D, multiplied by the vector v1, v2, minus lambda times the vector v1, v2, equal to the zero vector. If I want to factor the v1, v2 out, I can't just be left with A, B, C, D minus lambda. I need A, B, C, D, the matrix A, minus lambda times the identity matrix 1, 0, 0, 1. All of that multiplied by the vector v1, v2. So that if you were to do the distribution here, right, A, B, C, D times v1, v2 still gives us this, and lambda times the identity times v1, v2 still gives us lambda times v1, v2, because the identity matrix multiplied by the vector here just gives you back that vector, and then you still have lambda times it. So that's how we deal with that. We don't usually show all this work. We just say, oh yeah, this is going to be A minus lambda times the identity matrix multiplied by the vector v equal to the zero vector. So again, we're trying to solve this equation. Last class with me, we talked briefly about how your matrix equations can either have like one solution or no solutions or an infinite number of solutions. And we kind of want to, well, we would love to have interesting solutions here. But, sorry, brain. How do I say this the right way? So there's an easy solution, which is not interesting at all. The easy solution to this equation is that if this vector here is the zero vector. Because then your 2x2 matrix, whatever A minus lambda I is, times this zero vector will for sure be the zero vector. We don't care about that solution. An eigenvector being the zero vector is not at all interesting because any zero, I should say, the zero vector is kind of always an eigenvector because the matrix times the zero vector will always give you back a multiple of the zero vector. Kind of boring. So we would prefer more interesting solutions to this equation. We would prefer solutions where this is not equal to zero. But then for that to work, this part over here has to be not invertible. Because if this, so let me back up. If that's how it's meant. So if this 2x2 matrix over here was invertible, there'd only be one solution. Right? We've seen that before, how we talked about finding solutions to a system of equations. If the matrix is invertible, you just multiply both sides by the inverse, and you would get, unfortunately, the solution to be the inverse of A minus lambda I times the zero vector, but any 2x2 matrix times the zero vector is just the zero vector. So that's the not interesting situation that we don't care about. So we want A minus lambda I to not be invertible. In other words, or equivalently, we want the determinant of A minus lambda I to be equal to 0. And that is how we start finding the eigenvalues of a 2x2 matrix, or any matrix really, but specifically 2x2, is by taking the determinant of A minus lambda times the identity, where we don't know what lambda is, setting that equal to 0, and then solving for lambda. So when you're asked to find eigenvalues of a matrix, this is where you should start, by taking the determinant of A minus lambda times the identity and setting it equal to 0. So let's actually look at the, I don't love that example there. Yeah, let's look at the matrix that we were just looking at. So for the matrix A equal to 3, 6, -1, -4, we're going to find the determinant of A minus lambda times I and set it equal to 0. Normally, I would encourage you not to write this all out, but let me show you what we're going to get. So that's going to be the determinant of the matrix A, which is 3, 6, -1, -4, minus lambda times the identity, which is 1, 0, 0, 1. You want to do the subtraction first before you start taking the determinant. Here's what's always going to happen. You're always just going to end up subtracting lambda from each of the diagonal entries before you take the determinant. So this is going to look like the determinant of our original matrix A, and in each of the diagonal spots where the 3 and the -4 are, we're just going to subtract lambda. So 3 minus lambda, 6, -1, -4 minus lambda. And then you take the determinant in the usual way. It's going to be the product of the diagonals, 3 minus lambda times -4 minus lambda, minus the product of the off diagonals, 6 times -1. And we're going to set that equal to 0. Then we solve this quadratic equation by multiplying it all out. So let's see, we get negative lambda times negative lambda is lambda squared. We get positive 4 lambda and negative 3 lambda for a plus lambda. And we get negative 12 plus 6, which is minus 6 equals 0. Some of the time this will factor nicely, some of the time it won't. I will warn you, in 17C, you're going to see also a fair number of complex or imaginary eigenvalues. Those come up and we deal with them. So don't be afraid of getting kind of funky solutions to this quadratic equation. Here this factors nicely. It factors as lambda plus 3 times lambda minus 2 equal to 0. So our eigenvalues are lambda equal to -3 and lambda equal to +2. These are our eigenvalues. So, I'll say again, to find the eigenvalues, you take your original matrix, you subtract lambda from each of the diagonal spots, take the determinant of that 2 by 2, set it equal to 0, solve for lambda. Yeah. Say that one more time. So I think you actually walked in a little bit after I was describing that. Where it came from was the fact that we're trying to solve this equation. We want A times our eigenvector, which we're going to find in a minute, to equal a multiple of our eigenvector. So what we did was we brought everything to the left-hand side, and then we kind of wanted to factor out the vector V. But the problem is, if you factor that out, you're left with A minus lambda times V, and A is a 2 by 2 matrix, and lambda is a number, like 2 or -3. And we can't do that subtraction. So to make that subtraction work, and to still have this multiplication work, we say, well, we're going to make lambda into a 2 by 2 matrix by multiplying it by the 2 by 2 identity matrix. Because then, if you distribute this multiplication here is still A times V, which is that right there. And this multiplication here is still, well, if you do this matrix times that vector, it's just that vector, and then you get lambda times that vector, which is exactly right there. So we're just throwing it in there to make the subtraction work and still make the multiplication work. Cool. So that's how we find eigenvalues. After we find eigenvalues, we can find each eigenvector associated with each eigenvalue. And let's see, where do we want to start here? Sorry, one sec. Yeah. So even though we already know the eigenvalue or the eigenvector for lambda equal to 2, let's go ahead and show how we find it anyway. So let's say that lambda 1 is 2 and lambda 2 is negative 3. It's not really important which way you label them, but we usually like to label each eigenvalue as lambda sub 1 and lambda sub 2. So for lambda 1 equal to 2, we're trying to solve A times some unknown eigenvector equal to 2 times that same unknown eigenvector. And since we're calling this lambda 1, let's call this eigenvector V1. Let's write it out. So this is going to look like our matrix A, which is 3, 6, negative 1, negative 4, times the vector. I like to call it XY. Some people like to call it V1, V2. I like to call it V1, V2 because I feel like I'm already using V1 and V2. Equal to 2 times the same vector. So there's our A, there's our V1, there's our 1, there's our... Most of the time at this stage, well, I should back up. This matrix equation represents a system of 2 equations. 3 times x plus 6 times y equals 2 times x, and negative 1 times x plus negative 4 times y equals 2 times y. We almost always only ever need one of those equations. Usually we just use the first one. So the first equation says 3 times x plus 6 times y equals 2 times x. Isolate your variables, or bring all the x's to one side, all the y's to the other side. So I'm going to say, great, 6y equals negative 1 times x. And then literally pick any numbers for x and y, except for 0 and 0, and solve this equation. I'm going to make the same choice I already made, which was, sorry. Yeah, I'm going to pick, actually, I'm going to pick x equal to negative 6 and y equal to positive 1. That solves that equation, right? If y is 1 and x is negative 6, 6 times 1 equals negative 1 times negative 6. There are lots of other choices we could have made. So the eigenvector we are picking here is negative 6, 1. But literally any non-zero multiple of this vector is also a fair choice. So you could have picked positive 18, negative 3. Or, I don't know, negative 600, 100. And both of those are also eigenvectors for this eigenvalue. Because if you multiply your matrix by any of these vectors, you'll end up with a result that is twice that vector. So usually, more than having an eigenvector, what you really have is an eigenline. Any vector on the line that this vector goes through is also an eigenvector. So like when I draw, don't love this choice here, 1, 2, 3, 4, 5, 6, up 1. When I draw this vector here, that's my V1. Really, any vector that terminates on the line that includes that vector. Sorry, my picture is not looking excellent there. But any vector on this line, which is the line, I don't know, y equals what my slope is, negative 1/6 x. Oh, look, that looks familiar. If I divide both sides by 6, y equals negative 1/6 x. Any vector on that line is an eigenvector as well. It is fairly standard to make the choice where your x and y are the smallest possible integers, but that doesn't have to be a choice. Lots of people would prefer to make x equal to 1 and y equal to negative 1/6. Not me, personally. But I just want to really emphasize the fact that any multiple of your eigenvector is also an eigenvector for the same eigenvalue. Let's find the other eigenvector. So for lambda 2 equal to negative 3, actually, let me hold on for 1 second. Before we do that, let me just also point out that we definitely didn't need to use the other equation at all. If we had used the other equation, -1 times x plus -4 times y equal to 2 times y, we're still going to get the same result. We're going to get -x equal to +6y, and that's exactly the same equation as right here. So we're still going to get y equal to -1 and x equal to, y equal to +1 and x equal to -6 for a vector of -6. So really, either of the two equations should get you there. Very occasionally, one of the equations tells you nothing, and then you have to use the other equation to get there, but you only ever need one of them. All right, now let's look at the other eigenvalue, which was lambda2 equal to -3. So we're gonna do the same thing. Oh, yeah, we'll do the same thing. So again, we're just trying to solve a times some unknown eigenvector equal to our eigenvalue times the same unknown eigenvector, which just becomes our matrix A, 3, 6, -1, -4, times our eigenvector, which we're trying to find, -3 times xy. Just for some terminology stuff, this is more next quarter, but I'm just gonna say anyway. The line that I drew here that contains the eigenvector is called the eigenline. That's not super important for now, but it will come back probably next quarter. So let's do this one as well. Again, I'm going to use the first equation. 3 times x plus 6 times y equals -3 times x. Subtract 3x from both sides. 6y equals -6x. I do like to divide by a common factor if it makes sense to. I would reduce this to y equals -x. So I'm going to say that x is equal to 1 and y is equal to -1. Literally, you can just pick a number to plug in for x and then see what y is. So my eigenvector here is 1, -1. You don't have to check this, but it should be true that the matrix multiplied by this vector is a multiple of that vector, specifically -3 times that vector. Let's check it just to be sure. You take your matrix, 3, 6, -1, -4, multiplied by 1, -1. You get back 3 times 1 plus 6 times -1, and then you get -1 times 1 plus -4 times -1, which is equal to -3, +3, which is exactly -3 times the vector we started with. So it works. Well, so a few notes here. Note. An n by n matrix will have n eigenvalues. Some of them could be repeated, though. They don't have to be distinct. Not necessarily distinct. Not necessarily real. They could be imaginary. They could be repeated. All sorts of funky things can happen. But you definitely get n of them. So if you had a 3 by 3 matrix, it would have 3 eigenvalues. If you had a 7 by 7 matrix, it would have 7 eigenvalues. But most of the time, we just focus on the ones that are 2 by 2, because that's what we're definitely doing next week. So let's do one more example, because I want to show you one more thing, and also I want you to practice. So I would say, why don't you all right now try to find the eigenvalues for the following matrix. A equal to 2, 6, 1, 3. So I want you all to try finding or taking the determinant of A minus lambda times I, setting that equal to 0, and solving for lambda. The eigenvalues should turn out to be nice. I mean, integers. All right, let's see what we got. So we have the determinant of the matrix 2 minus lambda, 6, 1, 3 minus lambda. Again, every time you're doing this, you're just taking your original matrix and subtracting lambda from the diagonal spots. That's the easiest way to do it every time. We're going to get 2 minus lambda times 3 minus lambda minus 6 times 1. We multiply it out. You can show as much as will work here. I usually don't show very much, but if we actually multiply it out kind of a long way, I end up 6 minus 2 lambda minus 3 lambda plus lambda squared minus 6. And then putting it all together, I have a lambda squared. I have a minus 5 lambda, and the 6 is actually canceled. So lambda squared minus 5 lambda equal to 0. Factoring out a lambda, I get lambda equal to 0 or lambda equal to 5. The convention typically is to pick lambda 1 to be the largest thing you have and lambda 2 to be the other thing you have. But it doesn't really matter if you label them otherwise. So my eigenvalues are lambda 1 equal to 5, lambda 2 equal to 0. Let's find the eigenvectors. So a note about finding the eigenvectors. I like finding them the way I have mentioned, which is by, for lambda 1 equal to 5, say, okay, we're going to solve a times the vector equal to lambda times the vector. But that's not the only way to do it. And some people do like to do it a different way. So you can either do it this way, and I'm going to do it both ways for this one. So you can either say, cool, I'm going to do this, A, which was 2, 6, 1, 3, times the unknown vector xy equal to 5 times the unknown vector xy. And then use the first equation. You get 2x plus 6y equals 5x. Bring all the x's to the right. 6y equals 3x. Divide both sides by a common factor if it makes sense to. 3 in this case. So 2y equals x. And then here's the way I often actually think about the vector. X is just equal to the coefficient of y, and y is just equal to the coefficient of x. So what's the coefficient of y? 2. What's the coefficient of x? 1. Cool. So x is 2 and y is 1. Which makes sense, right? Because if x is 2, 1 times 2 is the same as 2 times 1. So if you make each thing the other thing's coefficient, you will always find the solution of this equation. Here's a different way people like to solve this. Instead of solving a times v equal to lambda times v, other people like to solve it as a minus lambda I times v equal to 0. So in this case, that would look like 2, 6, 1, 3 minus 5, 0, 0, 5 times the vector we're looking for equal to the 0 vector. I do not prefer to do it this way. But, or I should say, except or unless the eigenvalues are gross. So if the eigenvalues are nice integers, do it this way all day long. If the eigenvalues happen to be complex or even like irrational, like your eigenvalues maybe are 3 plus or minus the square root of 2, then often this way the computation is just a little easier. So you should skip this step though, and instead just say, well, we're just subtracting lambda from the diagonal spot. So I really should have written this as 2 minus 5, 6, 1, and 3 minus 5 times xy equal to 0, 0. The kind of more interesting thing about writing it this way, I think, is that both equations really, it's more obvious that both equations really are the same equation. These two equations, negative 3x plus 6y equal to 0, or 1x minus 2y equal to 0, I think we can more easily see that these are the same because the first equation is just negative 3 multiplied by the second equation. So these are the same equation, meaning they produce the same solutions. We still find the solution the same way. We're going to, get x equal to 2y, and then again, we're going to get our vector to be, oh yeah, y is 1, x is 2. So either way you do it is fine. I would prefer you did it this way because I think it's better. But the second way does have its advantages if your eigenvalues are not very nice. meaning not integers. We still have an eigenvalue left to find, or an eigenvector left to find, right? So this was our eigenvector for lambda equal to 5. For lambda equal to 0, well, then we're going to say that our matrix 2, 6, 1, 3 multiplied by our vector x, y is equal to 0 times x, y, which is kind of a special case, but not particularly notable. Doing the multiplication, we get, so I will point out, I could use either equation here. 2 times x plus 6 times y equals 0, or 1 times x plus 3 times y equals 0. I might as well use the one that has the smaller numbers. So I'm going to say 1 times x plus 3 times y equals 0. I'm going to say that that 3y equals negative x. And then my vector is going to be, well, x equals the y coefficient, y equals the x coefficient. Another reason I like using x and y is if you have to find the eigenline, you can just take this equation and solve for y. So if you actually divide both sides by 3 here, y equal to negative 1/3 x is the what we call eigenline. It's the line that if you drew any vector from the origin to any point on that line, it would also be an eigenvector for that eigenvalue. Wow, my lines are not that straight today. There's my eigenline, and here's specifically the eigenvector I'm thinking of, 3, negative 1. But really, any other vector that terminated on that line and began at the origin would also be an eigenvector. Cool. Let's do one more, and then we'll move on to the other thing, which I imagine he's going to get to before the end of the quarter. So one more example, which is actually super easy. What if my matrix A was equal to... sure. I mean, let me actually do one thing. I just want to check one thing. That's fine. No, I want that. Okay. Let's say my matrix was something like 3, 0, 2, 4. So I want to point out, well, actually, let's find it first. So to find the eigenvalues, determinant of A minus lambda I think you could even, well, no, I'll write it. I don't think you need to actually write the matrix. 3 minus lambda, 0, 2, 4 minus lambda. But check it out. We're going to get 3 minus lambda times 4 minus lambda minus 0 times 2. Okay, let's be wise here. You shouldn't do more work than you have to. This thing's already factored for you. Don't multiply it out. Please, please, please save yourself the effort, right? 0 times 2 is 0. Oh, look, it's already factored. So what are my eigenvalues? Yeah, you're right, 3 and 4. So lambda 1 is 4, lambda 2 is 3. Now, the shortcut for this is to make an observation. We had a 0 right here, which meant this part of the equation was equal to 0, which meant that these two numbers ended up being our eigenvalues. And that is true if you have a 0 in the upper right-hand corner or a 0 in the lower left-hand corner. If your matrix is what's called lower triangular, where everything above the main diagonal is 0, or if your matrix is upper triangular, everything below the main diagonal is 0, then your eigenvalues will always be the diagonal entries of the matrix. So, for example, if I said your matrix over here was B equal to, I don't know, 5, 1, 0, 7, you can automatically tell me that the eigenvalues are 5 and 7. Always true. As long as you have all zeros below the diagonal or all zeros above the diagonal, or both. The eigenvectors in these kind of examples are a little bit interesting. What do I mean by that? Let's take a look. So let's say we want to find them. Let's do lambda 1 equals 4 first. So lambda 1 equal to 4. we're trying to solve A times V equal to lambda 1 times V1, I should label it. So we're going to get 3, 0, 2, 4 times the vector we're looking for equal to 4 times the vector we're looking for. And in this one, well, let's see. The first equation gives me 3x plus 0y equals 4x. Okay, so I have 3x equal to 4x. What's the solution? 3 times what equals 4 times the same what? Three times the number equals 4 times the same number? There is a number. What is it? 0. 3 times 0 equals 4 times 0. But that's the only solution, right? Another way to solve this would be to subtract 3x from both sides and say that you get 0 equal to x. Cool. So if x is 0, that doesn't say anything about y, except it totally does. Because what did we say at the very beginning of this process never gets to be an eigenvector? The 0 vector. So if one of the components is 0, the other components can't. You can't have 0, 0, right? So that, again, you might miss this. So we cannot have 0, 0 as an eigenvector. Not because it doesn't work, but because it's kind of the case we just ignore. So 0, 0 is never something we consider an eigenvector because we care about the length of this vector multiplying, and the 0 vector, its length doesn't multiply, right? The 0 vector, if you multiply by 5, still is the 0 vector, still has the same length. But here, if x is 0, that means y can be anything not 0. So you could say your eigenvector is 0, 5, or 0, negative 7, or 0, 100. But the choice people typically make is the smallest possible integer, which is 1. You could make any other choice as long as it wasn't 0, 0, but the standard choice is 0, 1. All these eigenvectors point in the same direction. 0 to the right and 1 up, or 0 to the right and 5 up, or 0 to the right and 100 up, or 0 to the right and, well, 7 down points in the opposite direction, but that's the same enough. So once you have an eigenvector, any multiple of it is also an eigenvector for that same eigenvalue. Okay, for the other eigenvalue, things are actually a little bit more perplexing, I would say. For lambda 2 equal to 3, we have the following. 3, 0, 2, 4. Maybe not, actually. I could make an argument for either one being perplexing. But we have the same equation. So then if we try to solve this, this is the situation where the first equation doesn't help you. So our first equation is 3 times x plus 0 times y equals 3 times x. And this equation doesn't have a specific solution. This is true no matter what x is. So it doesn't help, right? This doesn't tell us anything about what x is restricted to be. We are not limited in any way. So great, that's not helpful. Move on to the other equation. 2 times x plus 4 times y equals 3 times y. Oh, that super helps. I have an equation here. I have 2 times x equals negative y. And so then I can say that my eigenvector is going to be, well, x is, I like to make the x part positive personally. So I would maybe, like, I'm going to say that x is, instead of saying x is negative 1, I'm going to say x is positive 1 and y is negative 2. That's just a personal preference, though. You could have easily said negative 1, positive 2, and still gotten an eigenvector. So really, really, really worth remembering that if your matrix has a 0 in the upper right corner or the lower left corner, the eigenvalues are just the diagonal entries. That is always true. But if you miss that fact, I would say, remember that when you're finding the eigenvalues, if you see this multiplied out and you see that this part's going to be 0 here, don't make the mistake of multiplying that out and causing yourself more work. It's already factored for you if you're just subtracting 0. Okay, let's see. Do I have anything else? Interesting. Oh no, I did something else. Okay, that's fine. Yeah, sure. All right, let's get to the real meat of it here, which is the iterated matrix multiplication. Yeah, we got yes, because that's definitely something I imagine he's going to try to talk about and put on your final exam. So we'll go there. So remember how we talked about Leslie matrices last week, and we talked about like multiplying with the same Leslie matrix over and over and over again. Well, the idea is that we'd like to have a way to do that a lot of times without having terrible calculations. We'd like to say like, here's our beginning situation, and here's our Leslie matrix, and we'd like to see like what happens after 100 iterations of the Leslie matrix. And there is a way to do that for most matrices. Not all. There are some matrices it doesn't work for because they don't meet a certain criteria, which is actually hard to quantify. But the ones we deal with will, so it's not a problem. But it does take a bit of building up, and the process is kind of weird. So let's walk through this example. I'm gonna try not to write down all things. So, example. We are studying a population divided into 2 age classes: juveniles and adults. Juveniles will be J, and adults will be A. And here is the setup. Juveniles have an average. Juveniles have an average of 2 offspring, while adults have an average of 6. Um, 50% of juveniles move on to adulthood. So our Leslie matrix is the following. So again, in the first row, we have all the numbers that are becoming offspring next year, becoming juveniles as our lowest age class here. So it's going to be 2 times the number of already juveniles plus 6 times the number of already adults. And then the number of things that make it to the next age category next year. Well, half of the juveniles make it to adulthood next year. And we didn't really talk about the adults because we're going to say that like adults just kind of stay adults. So we're going to say that, well, they all die eventually, right? There's nothing beyond adult. So this is our matrix. Let's call it A, even though we would often call it L. Question, yeah.
Usually assume that they don't know.
When they tell you they don't. Yeah, I know, it's yeah. But so yes, yeah. Yeah, I know. So let's say we're given an initial population. We're going to be given an initial population of J0, A0 equal to 100 juveniles and 80 adults. We can find subsequent populations. For T, we'll say years. I'm not really concerned about what the time interval is. So let's see what it is for T equal to 1. So T equal to 1, we're going to have that J1A1 is equal to our matrix A times J0A0, which is going to be 2, 6, 1/2, 0, multiplied by 180. Let's see, we're going to get 2 times 100 plus 6 times 80, and then 1/2 times 100 plus 0 times 80. So it seems reasonable that this is what we're getting based on how it was described, right? We set up our matrix. Really, we're just checking to make sure we set up our matrix correctly. Half of the juveniles from last year made it to adulthood next year. And then for every juvenile that there was, every juvenile on average produced 2 offspring. So we got 200 offspring or new juveniles, and every adult produced on average 6 offspring. So we got 6 times 80 is 480 more. So 480 plus 200 is 680. Okay, and let's do some labeling here. I'm going to call this vector here n naught. I'm going to call this vector here, n1. And what I want us to point out is that at this point here, note that n1 is equal to a times n naught. Let's do one more iteration. Let's say 2 years. So for 2 years, our n2 is going to equal our a times our n1, which is going to be 2, 6, 1 half 0, multiplied by our n1, which is 680, 50. Okay, it's going to be a little bit more work here. See, 2 times 680 is what? 1360. Plus 6 times 50 is 300. And then 1 half times 680 is 340. So we get 1660, 340. Now, what I really want to point out here is that this a times n1, I could have written as a times, well, n1 was a times n0, or n naught. So it's really a times n naught, which is a squared times n naught. So we might be thinking about how you could do repeated matrix multiplication to get the population size at any time value. For example, it seems reasonable to think that our n3 would be a cubed times n naught. And so on and so on and so on. So that we could say that nt, the population size after t years, is just going to be a raised to the tth power times the initial population vector. I will also point out, because it comes up often, what we're really saying is that next year's population size is equal to a times the previous year's population size. Oftentimes, problems will start by saying this and expect you then to be like, oh, well, this really just means that. That if you know that next year's population is a times the previous year's population, then the tth year's population is just a times a times a times a times a t times the initial population size. So these two things really mean the same thing, but they try to make you work for it. So this is what you really want to be saying, but this is kind of where they start you off often. Okay, but now here's the issue. A to a power can be computationally complex. So here's how we do this. And unfortunately, there's kind of two ways of doing this. And I don't know which way, if both, he's going to show you. So we'll try to get through both of them. They're the same, but different. Right. So how to specifically calculate a to the tth power. Find the eigenvalues and eigenvectors. So we're going to find the eigenvalues and eigenvectors. Also point out that the notes on Grant's website are obviously what I'm using. And if you feel like I've left anything out, you might go back and look at those later today, specifically the notes on eigenvalues and eigenvectors and this iterated matrix multiplication stuff. So here's what we know. For a 2x2 matrix, which is always what we're going to be dealing with, we have the eigenvalues, lambda 1 and lambda 2, with the associated eigenvectors, v1 and v2. And as a reminder, what that means is that your matrix A times your first eigenvector is equal to the associated eigenvalue times that eigenvector. And similarly, A times v2 is equal to lambda 2 times v2. So here's what we're going to do. We're going to make a new matrix, the matrix of eigenvectors. So let P, or we're going to create P the matrix of eigenvectors as columns. So P is equal to the first eigenvector in the first column and the second eigenvector in the second column. And what's great about this is we have the following. A times the matrix P well, A times the first eigenvector gives you lambda times the first eigenvector. So that's really going to be the first eigenvector multiplied by lambda. And then A times the second eigenvector is going to give you the second eigenvector multiplied by the second eigenvalue. I recognize I'm not saying all the words about how this matrix multiplication really does work, but it does work out this way. That if you multiply this matrix times this vector, you get lambda 1 times that vector back in the first column. And this matrix times that vector, you get lambda 2 times that second vector back in the second column. And yes, the matrix multiplication is in this order on purpose. Or in other words, A times the matrix P equals P times this matrix here we call the diagonal matrix D. It's a diagonal matrix because you only have non-zero entries on the diagonal and you have zeros everywhere else. Diagonal matrices are super cool. Well, they're not really that cool. They're super useful because the diagonal matrix raised to any power is really, really easy to calculate. So here's what we're going to do. We're going to then isolate A. Yeah. So we're going to multiply both sides on the right by P inverse. So A times P inverse equals P times D times P inverse. And then the P times P inverse is the identity matrix. And any matrix times the identity is just itself. So here's the gist. A is equal to P times D times P inverse. And here's where things are going to get easy. That's a D. So now check this out. A squared. Well, I'm going to replace A with PDP inverse. But when you square something, it's just itself multiplied by itself. So you have PDP inverse times PDP inverse. Let's look at the middle parts. What's P inverse times P? What's any inverse matrix multiplied by itself? Right. And then the any matrix times the identity is just itself. So you really have D times the identity, which is just D. So what you're really getting here is P times D times D times P inverse, which is just P times D squared times P inverse. But D squared is easy. Just as a point of interest, right? D squared being lambda 1, 0, 0, lambda 2 times lambda 1, 0, 0, lambda 2. Check it out. You get lambda 1 times lambda 1 plus 0 times 0, which is lambda 1 squared. You get lambda 1 times 0 plus 0 times lambda 2, which is 0. You get 0 times lambda 1 plus lambda 2 times 0, which is also 0. And you get 0 times 0 plus lambda 2 times lambda 2. Or in other words, when you square a diagonal matrix, each diagonal entry gets squared. Or more generally, a diagonal matrix to any power is equal to the diagonal entries raised to that power, which makes it really easy to calculate. So we can generalize this and say, well, cool. That means A raised to any power is just going to be PDP inverse times PDP inverse times PDP inverse that many times. But then all the inter P inverse P's are going to multiply to the identity, which are then just going to kind of disappear. So every P inverse P, right? This P inverse times P here, this P inverse times P here, this P inverse times P there. All the P inverse times P's are just identity matrices. They all go away, and we're left with P times D times D times D times D times D times P inverse. Or in other words, P times D to the Tth power times P inverse. So if you want to raise a matrix to a really big power, what we do is we rewrite that matrix as P times the diagonal matrix times P inverse, and then you just raise the diagonal part to the really big power and multiply it off. It's still pretty gnarly calculation-wise, but it's much less terrible than it could be. So, back to our example, which we had found the eigenvalues for. We certainly had not. So, back to our example of A equal to 2, 6, 1/2, 0. I would really like to know what n10 is going to be, which would be a to the 10th power times our n naught. A reminder, our n naught was 180. I know it sounds like it's 180. It was the vector 180. So to do that, we're going to calculate a to the 10th power in this way here. It's a bit much still. We still have to find the eigenvalues, the eigenvectors, make this matrix P, find the P inverse. So it's still going to be some work. So let's find the eigenvalues. Determinant of A minus lambda I is equal to determinant of 2 minus lambda 6, 1/2, 0 minus lambda. That's going to be 2 minus lambda times negative lambda minus 6 times 1/2. Set that equal to 0, and we get, let's see, negative lambda times negative lambda is lambda squared minus 2 lambda minus 3 equal to 0. Factor, you get lambda minus 3 times lambda plus 1. So eigenvalues are 3 and negative 1. Yeah, don't try to squeeze it in. So for lambda 1 equal to 3, we have our matrix 2, 6, 1/2, 0 times the vector we're looking for equal to 3 times the vector we're looking for. I always pick the first row just because it just feels natural. So I have 2x plus 6y equals 3x. Subtract 2x from both sides. 6y equals x. So we get our vector being y is equal to 1, x is equal to 6. Again, I'm just taking the coefficients and putting them in the opposite spots. For lambda 2 equal to the other value, which is negative 1, same deal. 2, 6, 1/2, 0 times our unknown vector equal to negative 1 times our unknown vector. So now I'm going to have the equation, ooh, that looks terrible. 2x plus 6y equals negative x. We're going to subtract 2x from both sides. 6y equals negative 3x. 2y equals negative x. So my vector is going to be, instead of picking x equal to, no, yeah, that's fine. X equal to 2, y equal to negative 1. Now we're going to make the matrix P. So P is just the matrix of eigenvectors. So P is going to equal 6, 1, 2, negative 1. It doesn't matter which order you write them in, as long as your matrix D's eigenvalues are in the same corresponding order. So since for my P, I wrote V1 first and V2 second, the matrix D, then P should not have an arrow over it. Sorry, that's bad. That's a matrix, not a vector. Sorry. Our matrix D, our lambda 1 should go first. So it should be a 3, 0, 0, negative 1. I do want to point out, because I kind of think it's cool. I do think it's worth noting that it really is true that A times P is equal to P times D. So you don't need to write this down, but just off to the side, I just want to show you. If we look at A times P for a second, A times P, 2, 6, 1/2, 0 times the matrix of eigenvectors, 6, 1, 2, negative 1. Look what we get. We get 2 times 6. Oh, wow. Let's actually do it, James, instead of making it for yourself. 2 times 6 plus 6 times 1 is 18. 2 times 2 plus 6 times negative 1 is 4 minus 6, which is negative 2. 1/2 times 6 plus 0 times 1 is 3. And 1/2 times 2 plus 0 times negative 1 is 1. And that's exactly 3 times the first eigenvector and -1 times the second eigenvector. So it's exactly 3, 0, 0, -1 times the first eigenvector and then the second eigenvector. So it really does work. Just want to make sure we see that. Okay, so then we need P inverse. This is why we spent time finding inverses. P inverse, you're going to do 1 over the determinant, which is 6 times -1 minus 2 times 1. And then you switch the diagonals, change the signs of the off diagonals. So that's going to be 1 over -8. -1, -2, -1, and 6. Often when I have a negative coefficient, I do like to distribute the negativeness to it and say that's going to be 1/8 times the matrix 1, 2, 1, -6. Okay, so finally, not finally, we're closing in on finally here. We have that our matrix A is equal to, I always forget which comes first, to be perfectly honest. I think it's P inverse first. Nope, it's P first. It's P D P inverse. And I usually just like to write the 1/8 out at the end. It really doesn't matter where that scalar goes. All right, so now here's what we're trying to calculate. We're trying to calculate n10, which is a to the 10th times n naught, which is going to be a to the 10th times the vector 180. So if I write this out, I'll point out that a to the 10th is going to equal p times d to the 10th times p inverse. So that's going to be 6 to 1, -1, 3 to the 10th, 0, 0, -1 to the 10th, and then 1, 2, 1, -6. There's 1. Kind of gross. I mean, I won't lie. This process is not like the easiest thing I've ever seen, but it is manageable. It's just a lot of steps. So to actually calculate this, here we go. It's going to be this. We're just going to leave 3 to the 10th as 3 to the 10th. But -1 to the 10th, you should not leave as -1 to the 10th. What's -1 to the 10th power? 1. Right? If you have a -1 or a 1 to a power, you should simplify it to either plus or -1 based on what your powers and your things are. And I would actually honestly move this 1/8 out in front of the whole process. It doesn't really matter where you put that scalar. Let's put it out here. And then we have this here. It's kind of terrible. What do I want to say about this? I feel like there's some things I want to say about this here. Let's see. Yeah, okay, so I would probably, you can kind of do this any way you want. If it were me, I would kind of do this part and this part at the same time. So I'm going to write this as 1/8 times. So this first matrix, I'm going to have 6 times 3 to the 10th, which just is what it is, plus 2 times 0. I'm going to have 6 times 0 plus 2 times 1. I have 1 times 3 to the 10th plus -1 times 0. And I have 1 times 0 plus -1 times 1. And then over here I have 1 times 100 plus 2 times 80, which is 100 plus 160. And I have 1 times 100 minus 6 times 80, which is 100 minus 480. And then we continue the multiplication. We get 1/8 times. Here's where it gets really gross. So you have this times this plus this times this. So this 6 times 260 is something. It's 1560, I believe. So you have 1560 times 3 to the 10th plus 2 times -380 is minus 760. And then you have 3 to the 10th times 260. Plus -1 times minus 380 is plus 380. Again, not the nicest thing we've ever seen, but not impossible to deal with. So, yeah, we should try to do the other thing too. So this is one way of approaching this, is if you want to find a to the 10th times some initial vector, you do this. You do p times z to the 10th times p inverse times your initial vector. And there is another way to do this though, which, yeah, I think we have the time for it. Sure. Alternatively, for n10 equal to a to the 10th times n naught, we can start by writing our n naught vector, which is 180, as a linear combination of the eigenvectors of A. Which is kind of a pain in the butt, but we're going to do it. So the eigenvectors of A, they disappeared on me. They're right there. So our eigenvectors were 6, 1, and 2, -1. Okay, this part is also, I mean, it's all gross. Sorry, it's all gross. It's just gross. It's going to be gross. So we're going to try to write this vector as a multiple of v1 plus a multiple of v2. So we're going to say, great, 180 is equal to some constant times the first vector plus some constant times the second vector. Solving this is kind of a pain, but not really actually. So let's rewrite it as a matrix equation. This is really the matrix 6, 2, 1, -1 times the vector C1, C2 equal to 180. Which we can certainly solve by just multiplying both sides by the inverse matrix. So this is your P, and then we're going to solve for the constants C1 and C2 by saying it's going to be P inverse times 180. Which again, I'm sure is going to turn out to be super lovely. Let's see, you get 100 plus 2 plus 160 is 260. That number looks familiar. 100 minus 480 is -3. So here's what we're saying here. We're saying that we can write this vector 180 as equal to C1, which is 260 over 8 times the first vector, plus C2, -380 over 8 times the second vector. Yes, I'm certainly aware that we could reduce those fractions, but I don't really want to because I want us to see the same thing. Normally we would. Okay, here's where we're going to go this time instead. So, yeah, we have 8 minutes. We're good. So we're trying to calculate something like a to the t times some initial vector. And here's what we just did. We just rewrote that initial vector as a combination of our eigenvectors. This is equal to now a to the t times C1 times our first eigenvector plus C2 times our second eigenvector. Okay, but there's something special about the eigenvectors. When you multiply a matrix by its eigenvector, you just get the eigenvalue times the eigenvector. And that's true if you keep multiplying by the matrix A. Meaning, if I did A squared times the eigenvector, well, that's A times the eigenvector. But A times the eigenvector is just lambda times the eigenvector. But that constant lambda can kind of live wherever it wants to live, right? Go out in front. And so what you really have is lambda 1 times A times the eigenvector again. And A times the eigenvector again is another lambda times the eigenvector. Meaning we get lambda 1 squared times the eigenvector. And in a very similar way that when you raise A to the tth power, you get P times D to the T times P inverse, right? You get just that middle matrix being raised to the tth power, which is easy to calculate. We're getting the same sort of thing here. Whereas if you raise A to the tth power and multiply it by its eigenvector, you end up just getting the eigenvalue raised to the tth power multiplied by the eigenvector. Kind of like how in the diagonal matrix, you also end up getting the eigenvalue raised to the tth power. It is not a coincidence. It is very much the same for reasons. So here's what's going to happen here. When you multiply this out, look what happens. We get C1 times A to the T times V1 becomes lambda 1 to the T times V1. And A to the T times V2 becomes lambda 2 to the T times V2. So I know it's a lot to digest. I'm sorry to have to go through so quickly and not have class on Thursday. But I wanted you to see it before you see it again tomorrow and or Friday. So to calculate the thing we're actually trying to calculate, which was A to the 10th times R and not, let me look back here real quick, making sure I'm not, right. So now we're saying that we're going to have A to the 10th times R C1, which is gross, 260 over 8, times our first eigenvector, plus C2, negative 380 over 8, times our second eigenvector. I'll remind myself that our eigenvalues were, what, 3 and negative 1. So this eigenvector was associated to lambda equal to 3. This one was associated to negative 1. So we multiply this out. This A to the 10th times V1 is going to end up being 3 to the 10th times our V1. And this A to the 10th times our V2, our second eigenvector, is going to be our negative 1 to the 10th times our V2. This is what I would focus on mostly, is that when you multiply the matrix by the sum of the eigenvectors, you get the eigenvalue to that same power. Now let's go back and look real quick. I know, I'm trying to say a lot here. If we go back and look at our results, do they look the same? I feel like I'm missing something. So disappointing. Oh no, we're good. So looking at back over here for a second, we see that, yeah, in my first entry, I have 1/8 times 1560, which is 260 times 6, times 3 to the 10th, plus negative 380 times 2, which is negative 760. And in my second row, I have 260 times 1/8 times 3 to the 10th times 1, plus negative 380 over 8 times negative 1 is the same as 380 over 1. Yeah, so they are the same. So we have the same result either way you did it. And it's kind of a very different way of getting there. Even though it's really the same thing, it feels like a very kind of different route. So both of these are valid ways of doing this. I imagine he's probably going to try and show you both of them. Yeah. So the takeaways here really are the following. For matrix A, with eigenvalues, lambda 1 and lambda 2, and associated eigenvectors, V1 and V2. We say associated because lambda 1 goes with V1, lambda 2 goes with V2. You can't interchange them. We can say the following things. We can say that A is equal to P D P inverse, where P is the matrix of eigenvectors, and D is the diagonal matrix of eigenvalues. A raised to any power, it can be written as P times the diagonal matrix to that power times P inverse, which really just becomes P times the 2 by 2 matrix lambda 1 to the tth power 0, 0, lambda 2 tth power. P inverse. Additionally, A to any power times a multiple of V1 plus a multiple of V2 can be multiplied out and end up with C1 A to the T times V1 plus C2 A to the T times V2, but then A to any power times an eigenvector is equivalent to the corresponding eigenvalue to that power times the eigenvector. So I would say these are kind of the takeaways from what we just talked about, is that you can kind of express these things. So then you can do this iterated matrix multiplication kind of either way you want. You can actually calculate A to the tth power and then multiply it with everything you want. Or you can say, well, I'm not really going to calculate A to the T, but I know when I multiply it by the vector that I have, it turns out to be this. The only hard part about this one is, for this one, we have to write our initial vector and not as a linear combination of the eigenvectors, which can be a little bit of extra work. All right. I wish I could say more, but time is fleeting. So as a reminder, we do not have class on Thursday. Be here. You might have noticed I haven't said anything about a practice final. I haven't written one. I tried to find his old one, but nobody. I thought I had a student who had it, but she did not, unfortunately, because it's not built. So I'm not sure exactly what I'm going to do. I will certainly try to get. I found a couple practice finals from other professors I have that have solutions written to already. So I think I'll post those for the moment and then think about what else I might do. Yeah. When's your final? Thursday. Okay. So good. That I might. So I can't guarantee I can get anything up in the next few days, but I think I could probably get something up on Monday of next week. I know that's kind of late, but it's probably the beginning. So I'll certainly get up the things that are already like produced, that have final exams written and solutions written. And then I will do my best on Monday of next week to get a practice final that maybe feels more geared towards specifically the Dell, written and posted, and then maybe solutions on Tuesday. That's my goal. That's my goal. And as a reminder, please, if you haven't already, do the evaluation on Canvas. If you have, thank you. If you haven't, do it. It's not that long. It's like just a few questions throughout the class. Yes.
I wanted to know if you could help me make something. So basically, I'm applying for like an assistant position for the summer.
What position?
Student learning assistant.
Okay. Let me stop the video here.